In this video, I'm going to be talking about Chapter 13, Nuclear Physics, Cambridge International Examination Syllabus from 2019 to 2021. This is for AS and A level, but I will be explaining in only AS level. We're going to be talking about all the syllabus in the syllabus of the CAIE from 2019 to 2021. Here's the summary of what we're going to learn. The alpha particle scattering is studied as evidence for the structure of the atom. The nuclear composition in terms of nucleon leads to the appreciation of mass defect and binding energy. And an introduction to a fundamental particle is going to be included. So this is going to be a summary of what we're going to learn. And here it's going to be all the lists that we have to cover up, and I'm going to be teaching every single thing, and no information is going to be lost. So every information I'm going to be explaining, and I'll try to explain very clearly. And I hope by the end of this video, or by the end of this full nuclear physics course, you should be able to master chapter 13, able to answer every type of question in nuclear physics. Before I move on teaching about nuclear physics, I want to give credits to all three books that I've studied, that I've learned to apply to this presentation. I try to make everything more simple and more understandable than the textbook, because some of the books were not followed by the syllabus, and some of them were like giving information about history and information we don't even need. So but I will be following all the syllabus, all the information very clearly, so you don't have to worry about extra information that you don't need to know. If you want these PDF or notes to send you by free, just subscribe and turn on notification, and just DM me and see more information in the description, and I'll send you these books for free. Okay, now let's move on. The first thing we're going to talk about is the atom. So the important thing about the atom is the central nucleus here. The central nucleus, or in your book you might be called nuclei or nucleus. They're all the same thing. A nuclei is quite common in textbooks, so you might see that word a lot. But what's important is that the central nucleus contains a proton and a neutron. Okay, and so this is the central nucleus that contains a proton here and a neutron here. And outside the nucleus is an orbit, and it has electrons. Okay, I know I draw the atom wrong. It's not supposed to look like this, but I apologize for my drawing. But this is basically what it's going to look like. It's going to have an orbit and electrons. Okay, and keep in mind that the proton is a positive charge and the electron is a negative charge. But we're going to be covering up these later in later parts, so you don't have to worry about not memorizing them. You should be able to understand them. I assume you already understand the basic of chemistry, so I'm just going to refresh your mind from what you learned from GCSE. Okay, so a nucleon number, okay, this is a very common word, nucleon, come from the word nucleus. So nucleon number / atomic mass, you might call it, refer it from chemistry, is basically the number of protons plus the number of neutrons. So basically it's the total or sum inside the central nucleus here. Nucleon, nucleus, and then middle here. Atomic / proton number, we normally call it proton number, just normally. It's basically the total number of protons, but we don't have that one characteristic for protons only, because proton number can also be equal to the electron number, but that's only if the proton number is equal to the electron number if the atom is balanced. If the atom is unbalanced, let's say it's a negative charge, then that means that the electrons could be higher or lower than the number of protons. But right now the proton number is basically the number inside the protons. In a balanced atom, the electron number is going to be equal to the proton number. We're going to refer back to this fact again later on. Isotope. So isotope is atom of the same element, same number of proton, but different number of neutron. This is in my textbook, in the 3 textbook. Isotope was quite complicated to learn, and I only just took small information out of it, only this sentence, because you should only just know this part of the syllabus. The syllabus didn't explain much more about this and more brief information, but what you should know is that if you want to compare 2 atoms, if the neutron is different, then the atom or one of the atoms is basically going to be isotonic or isotope. Alright, same element, same number of proton or electron, but different number of neutron. That's all you have to know. Now, a radioactivity. So, some of your book might call it nuclear process. If you're confused, nuclear process and radioactivity is the same thing. Nuclear process can be have many types: radioactivity, nuclear fusion, or nuclear fission. So radioactivity is one of them. So if you're confused, now you should know. Radioactivity is a phenomenon that has processed whereby unstable nuclei emits radiation. So basically, an unstable nuclei, going back to the atom, if the center nucleus or nuclei, I would say, it's unstable, then that would produce radiation. Okay, and one type of that radiation is called an alpha particle, and there's actually 3 types of particle, 3 types of radiation. We're going to call them particles because we're going to like draw small dots of them to have a good idea of what the radiation is going to look like. So these particles known to be smaller than atoms, and only 2 had relatively high kinetic energy. They didn't say only 2. I had this in my mind because high kinetic energy dependent mass and velocity. Since the third one, which I will teach you later, the third one has 0 mass. So only 2 had mass. So only 2 radiation had mass. So they're the ones that have high kinetic energies. So these particles known to be smaller than atoms. Okay. The 3 types. The reason why I'm teaching alpha particle first is because I want you to get an idea of the next part of what I'm going to teach, which is the Geiger-Marsden alpha scattering. You might see this the first thing you see in your textbook, and if you're confused on what it is, it's basically an experiment to prove the existence of the nucleus of the atom and to prove that the alpha particle is smaller than the atom itself. So that's 2 results that must be concluded. So um, the setup is very simple. A source of radiation producing an alpha particle. Alright, that's gonna hit in a thin gold foil. The thin gold foil can be made into very thin, so that's why they use gold. Okay, and we're gonna assume that this point has an atom. Okay, um, and most of the alpha particle is gonna pass through. Okay, like this, and you can be seen from the screen. But that's not exciting. What's exciting is that it's gonna deflect by the central nucleus. The alpha particle is gonna deflect from the central nucleus, like this. I will show you like a very easy way to imagine later on. But basically, you need to know the result. The result is that the most particle pass through. Some will be scattered, and some will be very few are deflected and not pass through. I shouldn't use the word deflected here. It's my mistake. But basically, the alpha scattering is going to reflect because of the central nucleus. So another way of seeing this experiment is imagine these red dots or red particles as an alpha particle passing through an atom. Okay, this is the point of view right now. So during the collision, the alpha particle is going to pass through the atom, and some will be, I would say, pass through the atom from the, pass through the orbit, and some will touch or hit the central nucleus, and therefore the result is gonna reflect. Okay, it's like hitting a bullet, a very small spot. Okay, it's like in a bullseye. All right, a bullet, it's gonna miss. Sorry, it's not gonna miss. It's gonna hit in many places. It might hit here, might hit here or here, but very few are gonna hit very close to the center because the atom is very small. Therefore, as a result, if the alpha particle hits 100% exactly to the central nucleus, it's gonna deflect, resulting in deflection, and it's gonna be more than 90 degrees. So that's how you understand the Geiger-Marsden alpha scattering, okay? And therefore, in conclusion of this experiment, we conclude that all mass and charge are focused in the center of the atom, and therefore the nucleus is small and very dense. Also, the nucleus is positively charged as the alpha particles are repelled slash deflected. Okay, and we were able to cover up this part, infer from the result of alpha particle scattering experiments. This is the wait, I should point at it. This part is from the syllabus for what you should know. We should be able to describe a model of the nuclear atom. We did that to include protons, neutrons, and orbital electrons. Okay, we should also able to distinguish between a nucleon proton and nucleon number. We should able to understand that the element can exist in various isotopic forms, and each with a different number of neutrons. I told you that isotopes can be a little bit tricky to understand, but it's very basic because in the book they teach me 3 pages of this, which can be all concluded into one. So it's not really that too important. But if I want to explain about isotope, it would be in another video. And that's it for this part. I don't want to make it too long, but sadly it does. It's been almost 13 minutes. So I see you in the next part.